Hello. This is a talk about Paperproof by Evgenia Karunus, me, and soon Anton Kovsharov will join too. So whenever we have some computation, we can have a visualization of that computation. And a logic would typically consist of a language, semantics, and deductive apparatus, and we can have visualization of each of those. So language is defined by grammar, and we can visualize it as a parse tree or a sentence diagram. Semantics is defined by some piece of code, and we can visualize it by a truth table. And deductive apparatus is defined by rules of inference, and we can visualize it in many ways. However, all of these ways share a common language, and it would look something like this. An automaton reminiscent of the derivations in formal logic textbooks. So in this automaton, each state is a sequent, and the rules of inference define legal moves from state to state, so from one sequent to another sequent. And we try to get from the initial state to some accepting state. So names of the derivation rules will be in gray, and we will call them verbs. Stuff to the left will be hypothesis, they will be in green, and stuff to the right will be goals, red. So these are the most popular visualizations of deductive apparatus. First one is natural language. Originally, it would be what you would see in math textbooks. It looks like this. And Lin's version is Linder Boss by Patrick Massot, or you can just ask GPT to describe your proof. And structurally, it's a mess. Like this is a parody of what you would see in natural language proofs. So just a bag full of goals, hypotheses, and verbs. That's pretty good. Then we have a visualization, which is a deductive proof. This is what you will see in most proof systems, and Lin's version is default info view. Structurally, it's better because we see what's hypothesis, what's goals, what are verbs. However, we don't see the full proof. We only see a partial proof. This is a single sequence at a time. Another visualization is a speech table. This is what you would see in logic textbooks, and Lin's version would be explored from MathLib by Mario Carneiro. And structurally, it's much better. It's a full proof. However, there is, and now verbs are always connected, like you can always follow it. But the problem is that all branches get condensed into a single column. So instead of having this nice 2D structure, you get a single column structure. And another visualization is a Gensen tree. And this is what you would see in logic textbooks. And it's a full proof, and the structure is pretty amazing. The only problem with it is that there is studious hypothesis scope notation, because sometimes you would have it repeated, all the hypotheses repeated, and sometimes you would have this, which is hard to follow. There is no hypothesis goal differentiation, and you cannot do proper top-down proofs because you cannot follow which hypothesis appeared first and which appeared second. So Lin's version, what would it be? Paperproof. And Paperproof fixes all the issues that I described above. So now I will show the demo of Paperproof. This is Paperproof in action. This is how we write a proof. So I start by sorry, then we do this. Notice how the right gets combined into, like, spreads out. So the right has to go like this. And the nice thing is that you can find, you can see the stuff that you wouldn't usually see. For example, when we have SIMP, you can see which hypothesis this SIMP ended up using. So out of these two, only this one was used. When you have calc, it's very obvious that it's a transitivity thing. So this repeats here, transitivity. It's also visible what Conger used. So this one used this one, this hypothesis, this one used this hypothesis. When you have your eyes, they're nicely nested under each other, so it's always visible how the tactic affected each hypothesis. This is a typical massive proof. Like I have to warn you that this is paper proof, the next version, which will be published in 3 days. In the previous version, it didn't work quite well in Maslib. Now it will work quite well in Maslib. So you see all red eyes get unwrapped very nicely. And combinations. When you have a combination tactic, it's clear what tactics were actually applied. So here it started with apply and .intro, and then it tried to do this again, and it succeeded. And in this case, it proceeded to like apply intro didn't work, so we did apply or and so on and so on. You can see it.
I think Patrick has a question.
Yeah, I'm sorry, I'm a bit dumb, but I have no idea how I'm meant to read those diagrams. So you keep saying this is clear and what happens, but I mean, will you
have no idea,
or is it meant to be obvious?
Diagrams, right?
Yeah, in any of the diagrams in Paperproof that you showed, I have no idea how to read.
Okay, so this is, we start from we start from the goals. Okay, actually, this will be visible in the Paperproof anatomy right now. Okay, so these are.
I have no idea whether I should read from the bottom to the top or from the top
Yes,
to the bottom.
Okay, this will be the explanation now. So stuff in yellow and stuff in green is hypothesis. So this is the info view. This is the goal. Goal will always be in red. And hypotheses are either in yellow or in green. And you always read the proof towards the middle. So this is what we call in lean top-down proofs. And this is what we call in lean bottom-up proofs. So it goes from both sides to the middle. And anything that's in scope is always highlighted. So when you're here, you can just look at the stuff that's highlighted. So this shows this history of the proof. This stuff in gray, h.mp, is the goal username. And grayish boxes, these boxes denote variable scope, but you shouldn't overthink it. Like this will just come naturally after you play with some time. Hypothesis colors, why are some hypotheses in yellow, why are some hypotheses in green? So there are 3 types of data in lean. First one is sorts, which we do not show at all. Because especially in Maslib, you'll have a lot of sorts that do not even belong to this proof, and they're really useful. Yellow ones is data, and you can usually run induction on it, and green ones are just much always useful. This is a proof. So goals form a tree because the way tactics works in lean, like first you would have a single meta variable, which would correspond to a single goal. And then when you execute some tactic, you assign to this meta variable some expression, for example, if.intro, and then you have 2 meta variables here. And these 2 meta variables correspond to 2 goals. So this single goal forks into 2 goals, this goal and this goal. So it always forms a tree here. Hypotheses do not always form a tree. Hypotheses form many little trees because we define what's under what just by heuristics. So if they have the same variable name, they will be under each other. And also depends on which variables appeared and which variables disappeared. So is there anything like this in other proof of systems? Not really. In code, there was proof 3 by Hendrik Truus in 2011. But for some reason, he didn't include hypotheses and goals, which is the most important thing here. He just used verbs, tactics, but still there is some structure. And in 2018, Hideyuki Kawabata created TRAF, and he does show goals. These are goals, but there are no hypotheses, there are no scopes. This is very similar to Gensen's case in that sense. So you always have to look here to see what hypothesis. So you only see the current state hypothesis wise, and you cannot do top-down proofs. In Isabel Mathematica, nothing. But you can implement Paperproof in other proof systems. So this is the structure of Paperproof. So you would have Paperproof lean package. That's why you need to do import lean when you use Paperproof. There is Paperproof VS Code extension. That's where you have to install VS Code extension. And there is a Paperproof rendering engine, which is about 4,000 lines. And this is about 200 lines. And to implement it in code, you would need to fully rewrite this, and this will stay as it is. So it's quite involved. Anton will describe how next. But after you rewrite this, there are only 3 lines to change in the VS Code extension itself. So when you see a lint proof, there are 3 ways to glean information from this proof. First one is just get texts, like just textual tactics. Second one is to get expressions, expors. This is what you get when you do print high. And this is used, for example, in Explode. It's very low level, just lambda abstractions and applications. But if you need information about tactic applications and about how the goals were changing and hypotheses were changing on this high level, then you need infantry. And infantry looks something like this. And when you do quite some work on it, then you would get a structure that's like this, that Anton will be describing soon. And this is used in the default VS Code info view. This is used in machine learning packages because they need to know how tactics will affect in the state, in the rule, for example. This is used in Electron, and this is used in Paperproof. So now Anton comes in.
What do you think? Should we go through intersection of sets again after we described everything? Hopefully it would be more familiar. Just to reiterate.
No, I think I'll just create, just go. I'll just create.
Okay, hopefully it wouldn't be too confusing. So you see my screen? I would talk how Paperproof works and then show off some of future ideas we have. So as Evgenia already said, Paperproof consists of 3 main components, a lint parser, the VS Code extension, and the React app. Lint parser adds itself to a lint language server. VS Code extension serves a React app, which renders the tree. And each time user cursor position changes, it requests lint language server to parse the proof tree again and sends it to React app. I would mostly talk about how parser works. So to describe how parser works, I'll first describe what is a proof tree. Then I will describe what is an info tree, which is a structure which lint compiler provides. And finally, I will describe how we can parse info tree to get a proof tree. Hopefully it would be interesting. It would clarify our tree a bit. And also I hope it's useful for anyone who tries to scrape more data, how proof develops, for example, to train their machine learning model. So to start with, let's look at this visualization in Paperproof for the example of commutativity of disjunction. So you see goals as a red nodes, and they transform by tactics at the gray nodes. So the tactic can refine node, like intro, it can bifurcate goal, or it can close the goal. And you can see this tree in purple here. And the tree consists of a notion I have called arrows, and arrow says what the goal was transformed into. I would use purple and orange to denote goals, and I would use orange when I want to highlight that this goal was formed after tactic application. Now to info tree. So the info tree is a lint compiler structure which captures information about the elaboration process. Elaboration process is something which turns syntax, which lint can be user-defined, into something which lint compiler can work with. And it consists of many elaborator functions. Some of these elaborator functions would turn syntax into expr, others would assign some meta variables or change goals. Sometimes elaborators would just do part of elaboration and then delegate further elaboration for a subsyntax to other elaborators. Let's look at the info tree with an example. So this is an info tree for this example. And you can see here, for example, elaborator eval tactic sequence, which was responsible for lines 17 to 20. And it delegated elaboration to eval intro and eval cases for line 17 for intro, and lines 18 to 20 for line cases. And that's where basically tree is coming from, because eval tactic sequence delegated to other tactics which put their info into a subtree. Here you see that the type of the node is a tactic info node, and every tactic info node has an information about what goals it had before tactic application and what goals it had after. So yeah, it's info tree shortly. And now let's see how we can parse it to get a proof tree. So first idea and like instinct is look at goals before, goals after in tactic info node. However, that wouldn't be enough to build a proof tree, and I'll show it with a couple of examples. So first example, let's say we have two tactics, swap assumption and a focus. And the pair of goals before, goals after for them is the same. However, first one closes the goal to, whether focus just temporarily hides it. Proof tree should be different, but pair is the same. Therefore, information just from pair is not enough. And second example, if we have a custom tactic which user defined and it somehow split goals into 3, 4, 5, and 6, we have no information from here which of these goals are coming from goal 1 and which of them coming from goal 2. To understand what we need to do instead, let's understand what goal is. So looking at the tactic info node, goals are a list of meta variable IDs. Meta variables in Lean are placeholders which had to be introduced at some point because we didn't know what's this part of the proof yet, and we couldn't specify it, so we put a placeholder. And they are stored in a meta variable context, which has all meta variables, and if they have assignment, their assignments to a term. And this term might transitively have other meta variables. Yes, and goals, basically a list of some meta variables which are unassigned, not necessarily all of them, as we saw in the focus case, just some goals which are interesting to users. So now, as we know about meta variables, let's see our examples and why it makes it easier to understand what's happening. So in our custom tactic, we now see an assignment to a meta variable and see that it was an interconstructor, which introduced new placeholders. Having these placeholders, we now know what goal 1 transformed into and what goal 2 transformed into, and we can extract arrows. Looking at our example of assumption versus focus, we now see an assignment for meta variable 2 here and no assignment for the focus, and we can have an arrow here and no arrows here. Interesting thing which Evgenia already mentioned, that we also know what hypothesis was used in the assignment and can draw an arrow in the visualization respectively. So that would mostly work for many proofs. However, it has a slight problem that sometimes it would generate disjoint proofs. Let's look at this in the example. So here we have this proof by cases. Don't look into the details. Just know that it proof by cases which have some proofs. That's only important part. And the tactic cases, looking at the high level, just closed the goal 1. And internal tactics it had, which generated subproofs, are disjoint. And therefore, we don't know how to connect them. And we need to figure out what the relationship between goal 1 and 2 and 3, why it's happening. So looking at the meta variable context after, we might have expected to find something like that, where we can establish relationship between meta variable 1 and 2 and 3. But what we could have found instead, that meta variable 2 and 3 assignments has been inlined in the context, and it just depends on what tactic author did. They could have called instantiate meta variables, and in this case, we would find this. The only reliable way for us to establish the relationship when meta variables on the right are unassigned, but we have no guarantee that the tactic author put this snapshot at this point in time when mvar2 and mvar3 were declared, but not yet assigned. Therefore, we would need to extract this information from somewhere else. And that's where the info tree relationship comes handy, because in info tree, the internal tactics of the cases, exact and rewrite. Yeah, just learned that the cases can have a rewrite. So all internal tactics would be in a subtree. And you can establish all the goals which has been created, especially ones which have no incoming edges. And these are the goals we need to establish relationship with. Therefore, we need to introduce a new set of goals which we need to connect the goal with. I call them spawn goals, and extended notation with square brackets where I put the goals 2 and 3. So now goal 1 would be connected with goals 2 and 3. To wrap up, let's take a look at the why all tactics are handled uniformly, why we don't have a special example for a tactic like half. So here in the example, for half, we would get the following arrow generated, that our goal 1 got transformed into goal 2, and 2 new goals, 3 and 4, was spawned to prove these subproofs. Goal is transformed after half tactic because we have new hypothesis, even though the type of the goal didn't change. Looking at the visualization, you can see that we did some prettification here. So for example, for goal 2, we didn't create a new node, and we displayed subproofs of the hypothesis above the hypothesis instead of bifurcating the goal. The condition when we could do this prettification is if goal doesn't bifurcate, like in our case, and the type didn't change. So the important part I wanted to show with this example, that the parser is agnostic of whatever tactic it is. So if user has defined a have-like tactic, which behave like have, it would still be rendered properly. Yeah, so this shortly how Paperproof works. And now let me show you some of future ideas. So one idea we had is to use Loogle to pass all the context and get a suggestion of what might be the next step. So for example, in a classical infinitude of primes example, how we could prove that this thing is prime. And if we search for the goal in Loogle, we would get the suggestion, which we can show in a Paperproof and can accept it from there. Similarly, we could integrate with a reprover. One other example is how we can navigate theorems. So we could have a proof, let's say infinitude of primes, and here we use some theorem. Min fuck is prime. We can hover over that, navigate there, then see other theorem, navigate inside, see proofs for inside theorems, and have a path with the breadcrumbs of where we jumped from and come back. And the final one is where we could use our proof and draw a sketch over it. So for example, here, I could see that, oh, yeah, I could cancel this 0, right? So if I just cross it, I would expect, we can use some GPTV to look at the our sketch over the Paperproof and suggest what change we need to satisfy this sketch. In this case, we want to cancel 0, so we would generate something like that. The next step, which I can think of, is I want to substitute this A into the goal. So I would draw an arrow and I will expect something to close the goal, something like this. Yeah, that's pretty much it. Thanks.
Thank you both. Beautiful stuff. Are there questions? Looks like David has the first question.
Hi, thanks. This is a cool demo. I'm wondering what are the goals of Paperproof with respect to what it enables users to have an easier time doing, and
Yes, you
how do
go-
you evaluate to the extent to which it does help them?
Yes, you just go to Mathlib or to any repo that you want to understand, and you have a lot of proofs in a single file, and you want to understand what this file is in general about. And like there are two choices: either you can look at the the types there, and you can click through every line to see what this proof does, or you can just click one time and you see all the types immediately, and you can read the proof as if it's normal mathematics. But lets you read a proof quickly, without clicking on it, understand what the proof does.
Thanks.
And also with respect to understanding what's it even doing, it gets clear once you look at the proof that you already understand and like just click around. So like after playing with it, it shouldn't be confusing.
I would say it's side effect, but many tactics are behaving like black boxes, and they pull some hypotheses, whether Paperproof can show which hypothesis was actually used and what this automated machinery generated as a proof, as you saw in the demo.
Thanks.
Jira, I think you're next.
Yeah, thanks. It's a very interesting demo. I'm kind of curious though. It seems like because you are trying to encode all of the information of the proof, in sort of one diagram, it seems like while it would be a very useful pedagogical tool, that it might actually be hard once you get, proofs that have, say, a lot of hypotheses,
Yes,
deep in the library.
Yes, exactly.
And
It was
it just,
horrible. Yes, it was
Sorry.
horrible. That's why we introduced. This is a version that will be published in 3 days. It's not online yet, and the previous Paperproof was pretty terrible. Like every massive proof was very wide. You wouldn't be able to use it. Now we introduced 3 types of hypotheses, and these just cut down the bits substantially. Usually, just like you have a default info view open, you can just have the same, like maybe twice the size of the default info view, and you would see everything. And also, I forgot to show it, but you also can now do a compact mode that removes all paddings, and you can also collapse certain boxes, and you can also scroll around. So now it's hard to find a massive proof that doesn't get shown very compactly.
okay, great, thanks.
Evgenia, do you want to show a demo of this compact and sticky scroll things while we have other question? Because I think it's very good.
Maybe just like other question, and then if nothing is left, okay.
Yeah,
Mario, okay.
let's hear Mario's question first and see how much time we have left.
Yeah, so I also had some difficulty reading the diagrams. I'm wondering, you showed a bunch of hypotheses, but it wasn't exactly clear which hypotheses associated to which goals. Like, you had arrows and boxes on top of other hypotheses. So, like, how is there an easy way to tell whether a given hypothesis is on a goal?
Yes. So basically, first of all, when you're proving something, then you always the hypotheses that you have available are always highlighted. You just see them, and they also sticky scrolls. So even if you're outside, you will always see them on top. But if it's static, if you're not in the proof, if you're just reading the proof, then there are these gray boxes with gray background, and they denote scope. And just like in real scope, you can go out of the box, but you cannot go into some other box. Once again, after using it, it becomes intuitive. You do not have to think about it explicitly, but this like dark backgrounds denote scope as if it were curly braces. You can always go out of the curly braces, but you cannot go into someone else's curly braces.
Thanks.